Great to see everybody. I think we'll get started. We have a quorum. Nikola,
Already
you want
42 people. That's very good.
Sure.
Nikola, you want to start? Oh,
Yeah,
maybe are you a co-host?
Yeah.
Oh, good.
Let's see.
Good.
Okay, is this working?
Yeah, it's good. Looks good.
Yes.
Yeah.
Okay.
So, welcome to everybody. And thank you for joining in. We have two talks today concerning quantum criticality in the ionictides. And so we're delighted to have Nikola Maksimovic to start off. Nikola, the floor is yours.
Thanks. Thanks for the introduction, and thanks for inviting me to give this talk. So I will mainly be talking about the magnetoresistance of the phosphorus-doped barium-122 series. I want to give a special shout out to my collaborators first. So I'm a graduate student in James Analytis's group, so special shout out to James. Vikram Nagarajan and Ian Hayes, the next speaker, were instrumental for the crystal growth and also data collection in this project. Alex Koshalev at Argonne did much of the theoretical modeling that I'm going to discuss. Thomas Schenkel and Yunbei Kim from Lawrence Berkeley Lab were involved in this disorder experiment that I'll discuss. And then John Singleton at the Mag Lab was basically there for all of the data collection in pulsed field. So let me give a brief outline of my talk first. I'll give a few slides of background of why it's at all important to measure magnetoresistance in high temperature superconductors or quantum critical metals. And then, over the past few years, there's been a series of experimental studies that have kind of built up this phenomenology that I'll describe and what the open problems are. And the bulk of my talk will be focused on presenting an orbital magnetoresistance model for explaining several features of the data seen in barium-122. In particular, the model is based on magnetoresistance in the presence of what I call quasi-particle sinks on the Fermi surface. These are either regions of very high Fermi surface curvature or very high scattering rate. And these are applicable to underdoped and optimally doped barium-122 respectively. Finally, I'll have basically one slide of potential applications to other high temperature superconductors. So of course, here's the motivation for magnetoresistance measurements. I've plotted here the very famous phase diagram of the phosphorus-doped barium-122 compound. Probably the most interesting thing about this phase diagram is that the material is a high temperature superconductor. And I think the second most interesting thing is the behavior of the electrical resistivity in the normal state. In particular, as you dope the system away from the antiferromagnetic phase boundary, there's a kind of qualitative change in the temperature-dependent resistivity. This is maybe more clearly seen in resistance versus temperature traces, where you can see a change from T-linear dependence of resistivity to more T-squared as we dope away from antiferromagnetism. And this suggests that somehow remnant antiferromagnetism or quantum criticality is really affecting the transport characteristics in this regime of optimal superconductivity. And this idea has existed for a while that the transport behavior of the normal state is actually somehow correlated to the strength of the superconducting state. Here I highlight a few modern papers on the topic, especially Ian Hayes's paper. Stay tuned for the next talk. Where you can kind of see correlations between transport coefficients and the superconducting state itself. So this is why it's important to understand transport. The issue is that much of the data in this most interesting regime is only available above 30 Kelvin, above TC. And generically, you start to see phonons come in at those temperatures, and it becomes very hard to separate out, okay, what is an anomalous source of scattering and what is a more conventional source of scattering. So the low temperature data is extremely useful for a transport measurement. And this is where magnetoresistance comes in. One way to get data at low temperature is to just put the sample in a giant magnetic field, and you can get a resistive signal once you kill superconductivity. There's an added bonus, which using magnetoresistance, you can to some extent evaluate anisotropies in the scattering rate or Fermi surface. But most of these goals are kind of contingent on having at least a base level understanding of the mechanism for magnetoresistance. And that's proven fairly difficult. So there's been several experimental papers on this topic. I would say this kind of started in 2016 with Ian Hayes's paper on phosphorus-doped barium-122. But since then, many quantum critical systems have shown qualitatively similar behavior. And there's kind of three main things that we can take away from the existing data. One is that the magnetoresistance generally has this kind of hyperbolic shape, meaning it's B squared at very low fields, but then there's an extended range of linear and field resistivity. The second is that it seems to be kind of disproportionately sensitive to temperature. This was noticed by Ian Hayes originally, where you can just scale magnetic field by temperature and resistivity by temperature, and it seems to capture all of the low temperature data very accurately. And then probably the most beautiful aspect of this data is it seems to apply fairly generically to a bunch of different materials. So I've shown some examples here: chromium arsenide under pressure, iron selenide, the sulfur-doped iron selenide, and then electron-doped cuprate. So any type of mechanism that we propose needs to be, in some sense, easy to generalize, or not super dependent on specific electronic structure details. So I'm going to focus on barium-122 in my talk. Like I said in the previous slide, many of the magnetoresistance studies have focused on this kind of region of optimal superconductivity. And rightfully so. This was the original motivation for magnetoresistance measurements. In my talk, I'm going to first focus on the spin density wave state, and then slowly move over to the quantum critical regime, and we can see how things evolve from the spin density wave state. So first, I'll describe our experiments on linear magnetoresistance in undoped barium-122. This is an antiferromagnetic metal. The resistance versus temperature follows fairly well a t squared plus t to the fifth dependence. Okay, this is something that you expect for scattering from antiferromagnetic spin waves. So we don't necessarily expect many anomalies in the scattering rate in barium-122, but at low temperature, we see a linear magnetoresistance over an extended field range. And this is reminiscent of what's observed in the quantum critical regime. So this kind of motivates us to look for a mechanism that's based on orbital motion rather than some type of anomalous scattering rate. Okay, so let me describe orbital magnetoresistance and then one simple change that you can make to this model to see H linear magnetoresistance over an extended field range. The typical way to understand magnetoresistance, at least in what's called the relaxation time approximation, is you apply an electric field to the Fermi surface. And then when you apply a magnetic field in a perpendicular direction, the Fermi velocity of the quasiparticles will be averaged over these orbits, cyclotron orbits. And for most Fermi surfaces, the magnetoresistance that you get looks something like this. Okay, it's B squared at low fields and saturates at high fields. And there's a very, very narrow range of H linear dependence, if it's there at all. It's really more of a crossover regime between these two different extremes. Okay, but we can make a simple change to this model. Here I'm showing simulations of the magnetoresistance of this Fermi surface. Let's say it's 2D. And what I'm going to do is increase the curvature. So you make these points more and more kind of cuspy, up until the point that it's completely a square. And if it's a square, then the magnetoresistance is linear down to zero field. This is a known mechanism. This has existed for a very, very long time. The idea is that when a quasiparticle is executing a Lorentz orbit, as soon as it hits this cusp, the Fermi velocity is rapidly shunted into a perpendicular direction. And so effectively, these regions act like quasiparticle sinks. And the fraction of the Fermi surface that gets affected by this quasiparticle sink is linear in field. It's just proportional to the Lorentz force. So it's actually fairly rare to observe a Fermi surface that looks like this. But we have good reason to believe that the Fermi surface of antiferromagnetic barium-122 may have these sharp cusps. Here I'll show a cartoon. So you have a whole Fermi surface at the center of the Brouillon zone, electrons, Fermi surface at the corner, and they get nested, imperfectly nested by the antiferromagnetic ordering vector. And when a gap opens up, you get these banana-shaped pockets with these regions of large curvature at the corners. To some extent, this has been observed in ARPA's experiments on barium-122. These are actually simulations of the Fermi surface, and experimental data can somewhat see these banana-shaped pockets. So our collaborator, Alex Koshelev, did a calculation of what the magnetoresistance of this, this type of shape in the Fermi surface of barium-122 will look like. Okay, and there's a few magnetoresistance parameters here, and they depend in a somewhat detailed way on the fermiology and the scattering rate and things like that. What we did is we went to low temperature and used some reasonable values extracted from literature or our own experiments for the scattering rate, and we're able to model the magnetoresistance data fairly well. So blue is the experimental data, and red is the calculation using these parameters. This is, you know, there's a lot of uncertainty in these parameters, so this should not be taken as kind of quantitative proof that the model is correct, but it's more of just a sanity check of the model. And something interesting to note about this is that these magnetoresistance parameters depend on the antiferromagnetic gap. That sort of determines how cuspy the Fermi surface will be. And then because that strong turning point region primarily dominates the magnetoresistance, the relevant scattering rate is the scattering rate near that cuspy region, as opposed to the average scattering rate on the Fermi surface. So you can see this when you do temperature-dependent measurements and extract the scattering rate from the magnetoresistance as opposed to the overall resistivity. The scattering rate near these cusps, near these kind of nesting points on the Fermi surface, increases much more rapidly as a function of temperature. And this is kind of expected. So as you increase temperature, spin density waves will be excited, and they cause higher scattering at points that are nested by the antiferromagnetic order. Okay, next up, phosphorus.
Sorry,
Yeah.
can I ask a question?
Sure.
How do you sort out the scattering rate from the magnetoresistance?
Yeah, so it's basically these parameters depend on scattering rate, and they depend on primarily the scattering rate in this vicinity of that turning point. So this model is the magnetoresistance only of this region, which may not have the same scattering rate as the rest of the Fermi surface. Yeah,
but the gap is changing.
The gap may change. That's correct. Yeah, yeah. So that is not taken into account in this plot right here.
Okay.
Yeah, that's a good point. So let me move on to the phosphorus substituted. So, right, you make a good point. So these plots are meant to be kind of qualitative illustrations, and at least at reasonably low temperature, we can believe that the magnetoresistance is primarily controlled by the scattering rate. And then as we phosphorus dope the system, okay, this kind of anisotropy becomes more and more pronounced. You know, in 19% phosphorus substituted barium-122, we see a very similar type of linear behavior in the magnetoresistance at high fields. And one of the interesting things about this highly anisotropic scattering rate is because the magnetoresistance is primarily controlled by these two parameters, and we observe that the temperature dependence is much stronger than the zero temperature value. So effectively, both of these parameters go as t squared, like the scattering rate, plus a relatively small constant. And this leads to a very simple scaling relation for the resistivity or the magnetoresistance, where you can divide the resistivity by temperature squared and the magnetic field by temperature squared. And we see that it fairly well captures the experimental data. Okay, And this is reminiscent of what happens in the quantum critical samples where, you see the scaling with magnetic field divided by temperature and resistivity divided by temperature. Although in this case, in this case, given the model that we've applied, it seems to be the case that this kind of hyperbolic dependence on field arises due to these quasi-particle sinks on the Fermi surface. And the scaling with temperature may be due to a highly anisotropic scattering rate. Okay. So, I've already hinted at this already, but as we move towards the quantum critical regime, this gap kind of closes, and also these points turn into regions of very strong antiferromagnetic scattering. This is called the hotspot model, and this is a very well-known theoretical model. But it turns out that these regions of very high quasi-particle scattering can also act as quasi-particle sinks. This has been explored by Achim Roche and Alex Koshelev as well. Actually, Alex Koshelev did this calculation of magnetoresistance specifically for the Fermi surface of barium-122. What he did is model the scattering rate near this hotspot as a Lorentzian, and the specific parameters of this Lorentzian are dependent on spin susceptibility as well as the scattering cross-section with these antiferromagnetic fluctuations. And the magnetoresistance that you get from this looks almost identical to the magnetoresistance you get in the previous model. It's basically B squared at low fields and crosses over to linear at high fields. Now there's a few experimental tests we can do. So here I show what this magnetoresistance parameter is, what it looks like. There's this coefficient, which is a very complicated function of spin susceptibility parameters in fermiology. It's very difficult for us to calculate this and compare it to experimental data because there's a lot of unknowns here. One of the things we can compare is the dependence of these parameters on the background scattering rate. So in this case, because these calculations are not done in the relaxation time approximation, the transport properties will depend on sources of scattering in somewhat of a nonlinear way. So if you increase the background scattering, that has this very unconventional square root scaling on the magnetoresistance parameters. And this is something that we can test. So what we did is took samples of optimally doped, the quantum critical barium-122, and irradiated them with alpha particles at Lawrence Berkeley Lab. Okay. And you can see the effect on the zero field resistivity. The effect is to basically increase the resistivity in roughly a temperature independent way. Okay, and then several of these samples were taken to pulsed field and were able to do a detailed disorder and temperature dependent experiment on the quantum critical barium-122. So shown in the black lines are the calculation curves, the modeling based on Alex Koshelev's model. And in all cases, we can do this simple scaling relation where we divide resistivity by temperature and magnetic field by temperature. And as you disorder the system, the magnetoresistance decreases overall, and the coefficients of the scaling function change slightly.
Nikola, do you mind if I interrupt just for 1 second?
Sure, yeah.
So you do this analysis for the magnetoresistance, but it seems like if I look at the temperature dependence, as you change the disorder, that will affect strongly the cold region contributions, right? So I'm somewhat surprised by this linear resistivity slope that seems to be, to a zeroth order, not too sensitive to the amount of disorder, which I would not have expected this cold spot, hot spot model to describe that.
Right. Yeah, so that is a good question. I think one answer could be that we're not in the right regime of temperature. Maybe you expect to see the strongest changes to the temperature-dependent resistivity below 30 Kelvin. Another answer is that the hot spot, cold spot model is not the correct description of the T-dependent resistivity. Mm-hmm. Right. Yeah, it's difficult difficult to say whether the disorder will affect the temperature-dependent resistivity in this low-temperature regime. Yeah, so
for the magnetoresistance, when you go to very high field, are you getting an H square, or is it still linear?
For magnetoresistance, when you go to very high field, you see H linear behavior.
Always. This
Yeah,
is very different. This is very different from the cuprates, because in the cuprates we did find the H square in very high fields.
I mean, to some extent, it depends on what temperature you're measuring at. So if you're at high temperature, you do see a B squared variation. So
I am speaking of measuring cases which are near the optimum TC in the cuprates.
Yeah, I know there's been certain cuprates, I think LSCO, where there's a linear magnetoresistance at near the optimal TC.
We also see it in very overdoped cuprates as well, the appearance of this linear magnetoresistance at high fields. But I think your point in IPCO is clear that it's mostly quadratic there, but it might be the field scale, as Nicholas says.
This is very strange, a very big difference.
Yeah. You need to, I think it's important to consider what the Fermi surface and scattering rate look like. Also, if you have very clean samples, the cold spots of the Fermi surface can give a significant contribution.
In the cuprates, when we we did a lot of work dirtying the samples, and when you dirty them, they are still square, H square.
Okay, that's interesting. Yeah, it's might be interesting to compare. So where was I? Let's see. Yeah. So okay. So we've done these calculations. Alex Koshelev did these calculations for temperature dependent and disorder dependence of the magnetoresistance, and in particular, the predictions of the model are a T-linear variation of these magnetoresistance parameters. This just comes from the fact that antiferromagnetic scattering is T-linear specifically at the hot region. And then the square root dependence on disorder. And we see a T-linear variation in these parameters, and also to some extent you can fit the disorder dependence with the square root function. Now you only have 3 data points. It's not the most striking observation, but you can easily test using Kohler's rule whether the disorder scattering rate adds in a linear fashion with all the other sources of scattering. One of the assumptions of Kohler's rule is that scattering rates add linearly. And at 4 Kelvin, as we change the disorder level in our samples, there's a clear failure of Kohler's rule. So this strongly points to an anisotropic scattering mechanism. So just to summarize, Alex Koshelev's model and calculation for this material is able to capture several features of the experimental data: the hyperbolic shape of the magnetoresistance, the linear variation of the MR parameters, and also this unconventional disorder dependence that we've seen in our experiment. Yeah, so that's the kind of the end of my talk. I've presented linear magnetoresistance in underdoped and optimally doped barium-122. And then we have an orbital model for this behavior, which is based on these quasi-particle sinks. In underdoped barium-122, these are regions of large curvature, which slowly evolve into hotspots. Okay. I will just mention that, while these calculations have been done for barium-122, we might expect this mechanism to generalize to other materials. So for example, let's say the cuprates, you may have regions of the Fermi surface that have large curvature. This is a tight binding calculation for neodymium doped LSCO. Or you may have regions of the Fermi surface that have a very high scattering rate. And these can both act as quasi-particle sinks and in fact give rise to linear magnetoresistance. This is from Brad Ramshaw and Louis Teifer's paper, recent paper on cuprate magnetoresistance. And they were able to observe, just simply using a Shockley tube integral, that the magnetoresistance in high fields can be linear if you have very anisotropic scattering. So that's the end of my talk. I hope I didn't go over time. Thank you for listening.
Great. Thank you, Nikola. Before I turn over this to the question answer period, I just want to announce that we will not have the seminars next week, but 2 weeks from now, we'll have Ian Gallis from University of Paris and Heike Fall from Stanford talking about nematicity and related issues. So with that, any questions, comments? Penchen, please.
Yeah, so I was, yeah, very nice talk, yeah, Nikola. Yeah, so I was very curious, does the MR effect in your case dependent on the current direction within the AB layer? I mean, which direction you're applying the current?
Yes, I have not studied in detail for underdoped samples whether it depends on A or B. In all cases, we're applying in the A direction.
Okay.
In optimally doped.
Yeah, it's tetragonal, right? Optimal dope doesn't matter.
Yeah.
Whether 45-degree makes any difference, because you're arguing that this MR effect is basically opening up the gap. You know,
right.
I mean, that has a particular direction, right? In real space.
It does, but I think if you have tetragonal symmetry, it shouldn't depend.
No, but I mean, if you apply 45 degrees, you know, then yeah.
Between A and B.
Yeah.
Yeah, I'll have to think about it. Maybe that's something to try. Yeah.
So your field is along C-axis, right?
Field is along C in all cases. Yeah.
Okay. Thank you.
Yeah, we have a question by Roma Hirompe. Please go ahead.
Yeah. Hello. Well, thank you for the talk. It's very interesting. On this slide, actually, if in the graph on the bottom right, if you would zoom in on low h/t, then you start to develop their deviations at low h/t, whereas in the sample without irradiation, you don't see such deviations. Do you have any explanation for that?
Yeah, I mean, I can tell you why this is happening. This is happening because the curvature of these curves is changing slightly. It's actually not perfectly T-linear. So especially in disordered samples, you start to see at high temperature, it kind of has this spoon shape. I can't explain to you, you know, why in particular you start to see deviations at high temperature in the context of this model. But it's a reflection of the fact that the temperature-dependent resistivity is changing slightly.
Okay. Thank you.
Yeah.
Nigel, please.
Yeah, beautiful work, Nikola. Thanks for your talk. So looking at this slide, clearly, you know, you have this sample with a residual resistivity well over 150 micron centimeters. I was wondering, it'd be very interesting to see, you know, how this evolves. I mean, do you have at least preliminary data on that, or is just the magnetoresistance too small to resolve this kind of scaling in that particular?
Yeah. Unfortunately, we don't have data because this was, you know, right about when we were putting this together is when the pandemic hit. So we were not able to measure these most disordered samples. That's something to do in the future. Yeah.
Does the disorder survive if you heat it up, or does it go away?
Yeah. Yeah. So all of these are heated up to room temperature after irradiation, or during irradiation. They're actually.
Okay.
Yeah.
So it could survive. All right. We'll watch this.
Simil, can I? Yes, Simil, can I?
Go ahead, please.
Yes, this system phosphodoped barium-122. Certainly, we know that it has multi pocket, Fermi pockets. But your picture concerning which pocket, and it's because we have the hole and the electron pocket here.
Yeah. So both pockets are considered. It's basically a scattering between these pockets. That's the scattering. So orbital motion will occur on both pockets.
You mean the scattering between the hole and the electron pocket, or within the pocket here?
This antiferromagnetic scattering occurs between pockets.
Oh, I see.
Yeah.
Okay,
that's right.
I see. So it's a
Question.
this scanning result has any relation to the superlinear resistivity? I mean the temperature dependence.
It's difficult to say. I mean, this is one of the kind of main questions, is whether you can recover the temperature dependent resistivity based on this hot spot and cold spot model. I don't think there's a good way to do that at present. So it's, in our work, we're not able to capture the temperature dependent resistivity.
I see.
Yeah.
Okay. Okay. Thanks. Yeah.
I would like to have a comment on that.
Yeah,
Make a
Hilbert.
comment. Okay,
Mhm.
because in this work of Achim Roche, he showed that if you are at a quantum critical point and have a disordered system, then the hot spot, cold spot interaction will be stronger. And because when you go away from the quantum critical system, or if you put in more disorder, then the system evolves into a different type of universality class. So the resistance, for instance, changes as with the temperature from T to the 3/2 to more almost linear behavior. And I was wondering whether you see any of that in your work.
Yeah, so this is kind of similar to the question that Chimiao was asking about the fact that we don't seem to see very significant changes in the temperature dependent resistivity as we disorder the samples. So, like you mentioned, Achim Roche's paper, you should see kind of qualitative changes in the power law with disorder, but it may be a question of we're just at too high of a temperature. We have to go through in detail through Roche's paper and see, what are the different temperature scales involved in these different scaling regimes. So it's not something that I have a good answer to.
Okay, well, thank you. Mm-hmm.
Yeah.
I still have one remark. Can I go on?
Yeah, go ahead, Farley.
This system being multi-band, in principle, the scatterings are not going to be the same for the various bands. So the analysis that is done, which is similar to that done in the cuprates, is done for a single band model, where you think that the band has the hotspots and the. So in any case, you also have other bands. So when you look at a resistivity or magnetoresistance, you are seeing things which are adding the conductivities of the various bands. And that makes it more difficult to analyze than the case of single band models like the cuprates. What do you think about that?
I mean, you're correct.
We have done very, very careful work on the cobalt 122 with Florence Rulli-Albinck, in which we have tried to analyze the transport in terms of two bands and two different scattering rates, etc., showing that they were very similar. And in fact, in that case, we find a t-square term and not even a t-linear. Here, all this is done as if it is a single band.
Yeah. So, so in your work, were you looking primarily at the temperature-dependent resistivity?
Yeah.
Yeah. So the thing about the magnetoresistance is it's true that you will get contributions from each band individually. Mm-hmm. The regions that dominate the magnetoresistance are actually these quasi-particle sinks. So in our work, we've actually completely neglected the magnetoresistance arising from these cold regions. Okay. You primarily consider this nesting point. So
you have to consider the band which has the nesting points and consider it primarily.
Yes. Yeah.
Okay.
Yes. Yeah. So there's not a one-to-one correlation between resistivity and magnetoresistance. Resistivity, you need to consider everything. Magnetoresistance is dominated by these very small regions.
Well, that's what you think.
That's what I think. Yeah.
But regardless, Henry, I think the magnetoresistance is really, really interesting, because if I just look at the temperature dependence of the resistivity, it looks very similar to all the other quantum critical like materials, heavy fermions, etc. And also, Penchant actually has E/T scaling in this optimally phosphorus doped case. That also looks quite similar to the other cases. So one could ask question, given these seeming universalities, does the magnetoresistance tell us some variations across these different materials? And
I
that,
agree. I am puzzled by the fact that you don't find H-square magnetoresistance at high fields. But okay, because this is the only thing you expect once you have eliminated all the quantum critical fluctuations, etc. Okay, this is hard.
if there's no more further questions, actually, thank you, Nikola, for staying within time, and it's a good model.
Thank you very much.
For
Nice
this.
talk. Anyway.
Very much, a very nice talk. Let's move